Welcome to today's GEOTOP-A lecture. Today our speaker is Claus Ernst of Western Kentucky University. He's going to tell us about the braid index of knots and links. Take it away, Claus.
Thank you, David. So it's a pleasure to be speaking here, and I want to thank the organizers who invited me to give that talk. The work I'm talking about is the work of several years, and there are some co-authors. Listed them there at the bottom. Yunan Diao and Gabor Hente and Peter Liu. So I want to start really simple. A braid. It's just a bunch of strings, which in this case I put these braids horizontal, and they have to move from left to right or from right to left, and they can't sort of turn around. And once you close these strings, you can get a diagram which sort of looks like this. And all the strings are circling around a common point, which is sort of in the middle of this blue component. We think of these braids as oriented. So if this is a link, all of these strands curve in the same direction around the center. And for a knot, that really doesn't make any difference. That's sort of automatic in the first place. The braid structure is quite old. There is Alexander's theorem, which was proved somewhere in the 1920s, and it essentially says any knot or link has a braid diagram. And the braid index is the smallest number of strands needed to represent a knot or link as a braid. The computation of a braid index is sort of difficult. It is an integer, a positive integer invariant. And we know of several such things. There's the genus of a knot. There's the bridge index. There's the unknotting number. And as all of these things, computation of the braid index is difficult. There's no algorithm that works for all knots and links. And there are many knots and links for which we do not know the braid index. Up to this point, I always said knot or links. I will, from now on, just say knots, and please, it should be understood, knots refers to knots and links. So how do we compute the braid index? So I'm going to outline the strategy. This strategy is not new, so other people have used that. And so the first thing we need is the term Seifert circles. And so if you have a knot or diagram and you smooth all the crossings, so in that top figure I have drawn a positive and a negative crossings and the smoothing, it's important to understand the smoothing respects the orientation. And then at the bottom I have a diagram of a simple knot, and the red things are the circles you obtain when you smooth all crossings. And these things have a name. They're called Seifert circles. And so why are Seifert circles important? Well, there's a theorem by Yamada, proved in the 80s, which essentially says the following. If you have a diagram with S of D Seifert circles, then there's a procedure which converts that diagram into a braid structure where the braid uses S of D strings. So you can essentially convert a diagram into a braid without increasing the number of Seifert circles. And there are some corollaries of this theorem, which are sort of immediate. So if you have a diagram and it has S Seifert circles, then that bounds the braid index above. However, the braid diagram itself uses just as many Seifert circles as there are basically strands going around in the braid. And so basically that means if you have a braid index B, then the braid diagram has B Seifert circles. And that means there is a diagram which actually obtains the braid index number of Seifert circles. And so the braid index is equal to the minimal number of Seifert circles, where the minimum is taken over all diagrams of that knot or link type. So that tells us that finding a good upper bound on the braid index is equivalent to finding a diagram with a small number of Seifert circles. So minimizing the Seifert circles is not easy. In particular, there's the question, how do you know whether the diagram you have has the actual minimal number of Seifert circles? And in the future, I will refer to the term reduction move as a move on a diagram that minimizes the number of Seifert circles. The other ingredient we need is the Homefly PT polynomial of a Noddle link. It's an invariant. It's a Laurent polynomial in two variables, C and A in my notation. And it is defined recursively. And so I have thrown up the definition of this thing, and I'm assuming that most of you are familiar with this, and it can be calculated. And so here is a expert from Mathematica using the knot theory package, where we compute the Homefly polynomial of the knot 10, 117. And you see this polynomial down there. And what we're interested in is the A span. And the A span is the highest degree of the A power minus the lowest. And so in our example, the A span, the highest degree is 0, and the lowest degree is -6, and so the A span is 6. So how do we use that? So D is a knot diagram, W of D is the rise, S of D is the number of Seifert circles, capital E is the maximal A power of the Homefly, lowercase e is the minimal power of the Homefly, and B of D is the braid index. And so we have several inequalities, which had been proven prior before we ever started with that. And so the capital E power is bound by the number of Seifert circles minus the rise minus 1. And the lower power, the little e, is bound by minus the number of Seifert circles minus the rise plus 1. And if you take these two inequalities and you form the difference of capital E minus little e, you see the rise cancels out. You get twice the number of Seifert circles plus 2, and that will then result in the Morton-William-Frank inequality, which you see below, that the braid index is bounded below by capital E minus little e divided by 2 plus 1. And that together allows us to formulate a strategy of how we want to compute the braid index. So we have a family of knots, which I denote with capital F. And then we need to have an expression for the highest A power and the lowest A power, which works for all families, all members of that family. And then the Morton-William-Frank inequality gives us a lower bound on the braid index. And then we need to draw a diagram for each member of that family, which realizes that bound by the number of Seifert circles. And then we have the braid index. So we don't actually need the full Homefly polynomial. We only need the highest and lowest A power. However, it is not enough to track these, because we also need coefficients in order to make sure that they don't cancel out. And so what is a coefficient? I will show that in just a second, but it's essentially a polynomial in the variable C. So this is the example I had before. And if you look at, for example, the capital E, you have two terms, minus c squared and minus c to the fourth, and those are the coefficients. And similar for the little e, you have coefficients of the highest and lowest power. And so we want to keep track of those as well. So the other difficulty which arises is that these reduction moves are sometimes very difficult to find. And the final comment I want to make at this stage is there are cases where this strategy fails, where this Morton-William-Frank inequality does not give you the braid index, and it will come up at the end of my talk, an example of such a thing. So we applied this strategy to alternating Montesinos knots. And so I want to first outline what these things are. So what you see in this figure is a drawing of a rational tangle. And the rational tangle has a vector associated with it. And so here this is 3, 2, 2, 3, 3. And if you look at my drawing there, and you look at the southwest and southeast, so the bottom thing you see is 3. And then if you go to the right, you see a 2. Move back to the center, you see another 2. And then you see 2 3s. And so that realizes that vector. And 56/191 is the continued fraction expansion of that vector. And on the right, you see the denominator of that tangle, and that gives you a standard to bridge knot. So rational tangle is the important term we need to know. And stringing in rational tangles, A1, A2, up to AS, and then adding a number of horizontal twists, that gives you a Montesinos knot. And so on the bottom of this picture, you see an example where on the very right, you see 2 horizontal twists, so that delta is equal to 2. And then you see 3 rational tangles, all of which are sort of drawn by this dashed boxes that shows you the 3 tangles. So we have a formula which gives you the braid index of such an object. And this formula is complicated. And I will walk you through some examples of this, and then I will take a break for questions. The important thing about this formula is that it allows you to compute the braid index using a minimal diagram. So here's my first example. This is a Montesinos knot, which are given by 3 tangles. And it is basically given as an alternating minimal diagram. So what is the first step in this algorithm? The first step is you need to put an orientation on this thing, because the braid index is an invariant of an oriented knot. And so the convention we have is that the top arc is always oriented from right to left, as shown. And then to put the rest of this orientation on there, you basically trace this out, this top arc, and that gives rise to all these other black arcs you see here. And if there are several components, you can orient any other component any way you like. So the only thing we have fixed is the top big arc on the very top has to be oriented from right to left. The second step is that we are looking at the ciphered circle decomposition. And that's what you see in this picture here. Now, the important part is that the top arc and the bottom long arc, they belong to 2 different ciphered circles. And that gives rise to 2 classes, M1 and M2. And if the top and the bottom arc belong to the same ciphered circle, then that's class B. The difference between M1 and M2 is the orientation. So if I go back, you can see that the top arc is oriented from right to left and the bottom arc from left to right. But the bottom arc could also be oriented from right to left, and that's the difference. So in our case, we're looking at class M2, meaning the bottom arc is oriented from left to right. So that's the second step in the algorithm. Then you look at each tangle. So it turns out that each tangle in this particular class of Montesinos link has to have a Seifert parity, which we call A2, which is sort of indicated on that figure on the left. And it simply means that when you smooth out the Seifert circles, these two huge Seifert circles go through the tangle as shown. And then there may be lots of small Seifert circles within the tangle. They're not shown. The third step is for each vector of a tangle, you look at the crossing signs. And so the tangle 1, 1, 2, 2, 1, 1, 1, 2, 2, if you look at the crossing signs, you get -1, -1, -1, 2, and -1. And then for each of these, you use the formula shown below, which we call delta 2 of a tangle. And the bij's are the entries of this vector. So in our case, the bij are -1, -1, -1, 2, -1. And the first term gives you the last entry, which is in our case a -1. And so 1 plus -1 is 0, divided by 4 is 0. And so this gives you the first entry 0. The second term is you look at the even entries in the vector which are positive. And so in our case, there's only one, namely the 2. You divide the 2 by 2, gives you a 1. And the third term is you look at all the odd entries. So in our case, that's -1, -1, -2. You total them up, that's 4, divided by 2 gives you 2. And so this value is computed as 3. And then you do the same thing for the other two tangles. I will not go through this, but you see what we get. We get 1, 1. And then the formula says the braid index is 1 plus what you computed for each tangle. So the braid index is 1 plus 3 plus 1 plus 1, which is 6. So notice the only thing we needed to compute the braid index here is essentially the minimal diagram. It has to be an alternating Montesinos link. And then we need to essentially compute the signs of the crossings and then just plug it into the formula. I'll do one more example. This is of the class B. And what's the difference in the class B? Well, the difference in the class B is now the bottom and the top long arc belong to the same Seifert circle. And that automatically means if the top arc is oriented from right to left, the bottom arc is oriented from left to right. And then you can have different parity Seifert circles, different Seifert parity tangles. And so there are some of Seifert parity 3 and some of Seifert parity 2. And you see the formula there on the bottom. So the first thing I want to talk about is this delta naught. What is that delta naught? Well, there's a formula. It's essentially computed by take the number of tangles of Seifert parity 3. There are 2, so that gives you a 2. Those are the 2 tangles on the left side of my picture. To this, you add the number delta, which is 2 horizontal twists on the very right. So that's 2. And then you subtract the minimum of nu plus delta over 2 minus 1 comma delta. In our case, nu plus delta over 2 is 2 minus 1 is 1. And so the minimum is 1. So you get 4 minus 1, which is 3. So that's part of the computation. The next part is very similar to what we had before. For each tangle of Seifert parity 3, you look at the signed vector, and then you have a formula. The formula is more or less the same as the formula we had before, with the exception of the very first term. The very first term is, there's subtle differences. So in our particular case, we have -1 plus the sign of the last entry, which is -3. So that's -1 plus -1 over 4. That gives you the -1/2. The next entry is the even entries divided by 2. So you only have a 1 divided by 2 gives you plus 1/2. And then the odd entries, which is -1 and -3, which are negative. So that's -4. The absolute value is 4 divided by 2 gives you 2. And so for this tangle, we compute 2. The next tangle has a signed vector of 1, 2, 3. So -1 plus 1, that's 0. There's only one positive term in even position, that's a 2. That gives you 1. And then there's no negative term in odd position, so that's 0, so get 1. And for that second tangle, we use delta 2, and that goes in the same way as I have done before. And then you essentially have your formula. So delta naught is 3. The tangles contribute 2, 1, and 3. And so this thing has a braid index of 9. So again, we only needed to do the Seifert circle decomposition and then compute the crossing signs. And from that, we can read off the braid index. At this stage, I want to sort of take some questions. I want to tell you what is the rest of my talk. I will talk a little bit about the proof of the theorem. And then I will sort of talk a little bit about the non-alternating case, which is much, much more difficult. So I'll stop here and see if there are any questions so far.
So Klaus, I got a question. Is the braid index additive under connected sum?
Yes, it is additive under connected sum. There is a formula which says, I think you get braid index of the first component plus braid index of the second minus 1. Okay, I hear no other question. Is it okay if I go on?
Yes.
Okay. So I want to talk a little bit about the proof of this. So the first thing is I want to talk about this on the diagram side. And what you see there in these two figures are basically a bunch of half twists. And the important thing is that these strands in these half twists are antiparallel. What does that mean? Well, you see the Seifert circle decomposition, and you can see that essentially there are lots and lots of Seifert circles. So if you have 6 crossings, they're going to be 5 Seifert circles. And if they're an even number of, there's always one less Seifert circle than there are a number of crossings. And the error changes this figure to a figure where the number of Seifert circles is reduced. And basically, this reduction is done by simply rerouting one of those arcs. And you can see that on the left side, we have 6 crossings with 5 Seifert circles. There are reduced to 3 Seifert circles. And on the right side, we have 5 crossings with 4 Seifert circles, and they're reduced to 2. And so we call these moves MP Murasugi-Precitzky moves. Why is that? Well, those two guys have studied the braid index. They have essentially used the same idea of using the Home-Flat polynomial and reducing the number of Seifert circles in the diagram. And so that's why we call these MP moves. This figure here, I want to only show you that there is one different kind of reduction move in here. And if you look at this diagram on the top left, okay, and you see that there is an arc which sort of goes all the way around the diagram and then sort of comes back. And so there's an overpass, which was there on the top left, which has been rerouted. And the reason I want to point that out, the moves which I have shown you here, they're sort of local. They sort of just happened within the strand of anti-parallel twists. This move here is sort of global in the sense that it affects the whole diagram. The nice thing is that for alternating Montesinos knots, the moves which are possible to reduce the number of Seifert circles are very simple. They're either these simple moves applied to these anti-parallel twists, and then there is on occasion one global move, but only one. And so they're quite simple, these reduction moves. So that's the first part of how to get a diagram with a minimal number of Seifert circles. The second part is to look at the Holmfile fly polynomial. So a diagram has a lone crossing if there are two Seifert circles which meet at a single crossing. So for example, here, if I have these anti-parallel twists and you see these Seifert circles which just are connected by a single crossing, these are all lone crossings. So anti-parallel half-twists generate lone crossings. A diagram which does not have a lone crossing is called an elementary link diagram. And Yuan and Diao proved the following theorem. If you have an alternating elementary link diagram, then the largest power and the smallest power are given by this simple formula. The number of Seifert circles minus the rise minus 1 and minus the number of Seifert circles minus rise plus 1. And in addition, we know something about the C powers, the highest and lowest C powers. I do not want to go into details of what this formula actually is and what this exactly stands for. The only thing you should see from this, there is a formula for the highest and lowest C power. Furthermore, we notice that if you have an elementary link diagram, there are no reduction moves. So the number of Seifert circles in such a link diagram automatically gives you the braid index. And that follows because when you look at capital E minus little e, and you see the rise cancels out, you get twice the number of Seifert circles plus 2. Divide that by 2, minus 2, sorry. Divide that by 2, and you have the number of Seifert circles minus 1 plus 1. And so the bound gives you the number of Seifert circles. So what we want to do is to basically generalize this formula here to diagrams where reduction moves are possible. And the generalization you see there at the bottom. And so an additional term has been added or subtracted in this formula. And this is twice the number of reduction moves, either as a minus or a plus. Now the superscript R minus are the reduction moves that involve negative crossings, and R plus are the reduction moves that involve positive crossings. So remember, a reduction move was basically rerouting a strand, either an overpass or an underpass at a single crossing. And so the sign of that crossing gives a sign to that reduction move. And we essentially call a Murasugi-Pritsitsky link diagram a diagram which satisfies these two equations here. If a diagram satisfies these two equations, then it automatically tells us that the bound given by capital E and little e will be the braid index. And how do we know that? Well, because we have the number of reduction moves. And once we carry out these reduction moves, then essentially this is sort of an elementary link diagram, and there are no further reduction moves, and the bound of E and capital E and little e will be sharp. And so our goal is to establish this these two equations starting with an elementary link diagram. So I want to give you several examples, and I will not go through the details. Essentially, what we're going to do is we're going to use induction over and over and over. So if you look in this white formula in the middle, so the way we're going to use this is as follows. So suppose we know something about d minus and d naught, then we can draw a conclusion about d plus. So if we know the e power of d minus and the little e power of d minus, and likewise we know the same two powers for d naught, we can draw a conclusion about the highest and lowest power for d plus. The only thing we have to worry about that these powers do not cancel. And it turns out it is sufficient to track the coefficients, actually the highest and lowest z powers in the coefficient, in order to ensure that there is no cancellation. So I now will show you a couple of pictures of how we're going to use induction in such a scenario. So here is a circle of, so to speak, Seifert circles. So imagine that each of these shaded disks is an elementary link diagram. That is, each of these shaded disks represents a diagram where there are no lone crossings within that diagram. And then we sort of start gluing this together in such a way that we have a circle. And these things are connected by either a single crossing or by more than a single crossing. And obviously, such a diagram suddenly, like if you look at, for example, C4 and C5 at the bottom, that crossing here between those two is a lone crossing. And so basically, we do an induction on the number of circles in this figure. So in this case, there are 6. And then basically, we connect each of them by a single crossing, compute the highest and lowest power, and then we do an induction on if we add additional crossings. So for example, between C1 and C2, there are 3 crossings. And so you can add crossings one at a time. The thing is that when you look at a smoothing of one of those additional crossings, then basically the diagram either turns into a connected sum, or it basically gives you falls apart altogether. So the point is that we know exactly what happens to the home fly polynomials under connected sum operation. And so we can make statements about what happens to these diagrams. Another example is the following. So if you look at the top figure, so to speak, first. So you have a long straight line, that's a Seifert circle. And suppose you want to add additional Seifert circles as shown. Again, we do an induction on the number of Seifert circles you add, and then on the number of crossings each Seifert circle has to connect to this particular arc. There are some complicated details which you see more or less on the right side of this top figure, that basically these crossings are allowed to interweave. What you see there on the top is that if you were going to look at the orientation of these crossings, they're sort of parallel half twists. And then on the bottom, we basically use the top figure and we add anti-parallel half twists sort of as shown. And again, an induction on the number of circles you add, one circle at a time, sort of allows you to proceed. And sort of my last slide here is, think of a Seifert circle C, and you just add sort of anti-parallel half twists in any manner you like, as is shown there. And again, induction on the number of things you add sort of does this. The induction itself is quite tedious, and I don't want to really, or it's difficult to follow, and so I don't want to go into details, but that's essentially how this proof works. The reason this is possible to do for these alternating Montesinos links is that when you take a crossing and you smooth it or you change the over with the underpass, then whatever link you get remains in the class of alternating Montesinos knots or in the class of connected sum of two bridge knots. And there you know exactly what happens to the breadth of the home flat polynomial. Okay. That's all I want to say about the proof of that. I want to now move to the non-alternating case. Are there any questions at that point? Okay, hearing none, I'll move on. So the first observation is the following. Any reduction move that we found for an alternating Montesinos diagram can also be done in the same way.
Sorry, Klaus.
Yeah.
Jason Cantarella raised his hand.
Okay.
He might have a question. Jason, go ahead, Jason.
Oh, hey. So, I mean, non-alternating seems super intractable. So that seems like so much harder that it would be difficult to get any of this to work. But maybe this is a question for like after the talk. But I just hit my raise hand by accident because I was surprised that like this was going to work at all. So does it work?
No.
Okay.
Your intuition is quite right, but we have made some partial progress. Okay.
Oh, very cool. Okay.
And in the non-alternating case, there are actually cases where the Morton-Brown inequality isn't sharp.
Okay.
So I'll get to that.
Fair.
So my observation was that any reduction move basically that can be made on an alternating guy can also be made on a corresponding non-alternating guy. And so it immediately becomes apparent that the braid index of a non-alternating Montesinos link is less or equal to the braid index of an alternating Montesinos link. Then I was looking at a couple of examples, just sort of naively. This is from NotInfo, a Montesinos knot consisting out of 3 tangles, and you see there I made each tangle negative. And so I was just looking at the braid index, and we found, oh, the A breadth is 10 for all of these, and the braid index is 6. Wonderful. It's the same. And then here's another example, 12A 145. And there we found that the braid index for the non-alternating guys is 1 less. But nevertheless, in all the examples you can sort of look at it, NotInfo, that's what you find. Either the braid index is the same or the braid index is 1 less. And so that naively led us to think, oh, wow, there's something here that can't be too bad. And so we started on this, and we realized that, that was overly optimistic. So we restrict ourselves to pretzel links, which is the simplest case of a Montesinos link, where essentially each tangle consists just of a bunch of vertically arranged crossings. A couple basic observations about these guys. If each of the crossings in these vertical strands, if there are at least 2 crossings in each of them, then that's automatically a minimal diagram. You can permute these tangles any way you like. It does not affect the home fly polynomial. That can be done by mutations, for those of you who know what that is. And there are 3 types of pretzel links depending on the Seifert circle decomposition. So let me explain that to you. So here you see the type M1. That is the top arc, as before, is oriented from right to left. There are two big ciphered circles involving the top and the bottom arc. They're both involved from right, and the bottom arc is also from right to left. That's what we call M1. And these things are realized if all columns have anti-parallel orientation and essentially an odd number of crossings. And here you see that from the formula for Montesinos links, we know that if the alternating, if this thing is alternating, for example, all crossings are positive, we get 2 plus the summation of these alpha j's. So it's a straightforward formula. The second type is, again, the top and the bottom arc correspond to two different big ciphered circles. And the orientation of the bottom arc is from left to right. That happens if all the columns have anti-parallel orientation and an even number of crossings. And down here you see in the alternating case, so if there are only positive crossings, you get 1 plus the summation of the alpha j. If there's only no positive crossings, you get 1 plus the summation of the beta j. So that's M2. And the most complicated case is the case when basically you have a single gigantic ciphered circle. And then you have essentially columns which have parallel orientation and columns with anti-parallel orientation. And in order for orientations to work out, we have certain restrictions. So if you look at the symbol we have there, the nus and mus, those are columns with parallel orientation. The alphas and betas are columns with anti-parallel orientation. And the nus and mus have crossing signs as indicated. So the first ones are positive, the next ones are negative, and the alpha and beta in the same way. In order for this orientation to work out, the total number of parallel columns has to be even. So this is this, oh, my notation is inconsistent. It says K plus plus K minus. It should say rho plus plus rho minus, that has to be even. And then the number of antiparallel twists, that always has to be even. So this is the most complicated case. And even in the alternating case, there are crossings with opposite signs. So I will only talk about this M2 case because it's the simplest, and this case because it's the most complicated. So let's sort of throw out a formula in the non-alternating case. So if the number of positive and the number of negative columns, each of these is at least 2, you get a very simple formula. The summation of the alpha j plus the summation of the beta j. And that's just 1 less than what the formula would be in the alternating case. The interesting case is if you have a single column of negative or a single column of positive half twists. And you get this formula below. This is kind of complicated, so I just will walk you through some examples so you see what this formula actually says. So if I look at P 14, 14, 10, and essentially if everything has the same sign, then the formula for the braid index says you get 1 plus half of these entries. So 1 plus 7 plus 7 plus 5. And so for the alternating case, the braid index is 20. Now, if you have 14, 14, negative 10, that is that basically you have 2 positive columns, 1 negative column, and the beta 1, that's 5, is less than the minimum of these alphas, which are 7. Then you just get the summation of the alphas. 7 plus 7 is 14. And if you have 14, 10, negative 14, that has a braid index of what? Well, now it's the second case that beta 1 is 7 and that's greater or equal to the minimum of the alpha j's, which is 5. And then you get 1 plus the summation alpha j plus beta 1, and that turns out to be 15. And so what we see here is that the difference between the alternating and the non-alternating case is large. And basically, you can generalize these examples and can make that difference as large as you want. So why does this happen? Why does things become so complicated? Well, before I go there, actually, I want to sort of talk a little bit more. So in these the reduction moves are sort of initially the same as before, except now, for example, if we compare the 14, 14, 10 with 14, 14, negative 10, you see there's a difference going from 20 to 14. So there have to be additional reduction moves. What are they? And these additional reduction moves are shown in this particular figure. So this is 6, 8, 8, negative 6. And what you see there is going in that from that first error, then you see that we took that arc which was at the bottom and sort of retracted it. And then you see an error with dash, dash, dash error, and you see that a whole bunch of more complicated moves has taken place. And essentially, we were able, with these moves, to eliminate the rightmost column of these negative 6 twists completely. Now, if you look at this figure, you see that some of these arcs are sort of, these overpasses are sort of bold. They're sort of a little thicker. And wherever they are a little thicker, we can still carry out a move of this particular type of an MP type, which we have not drawn because then you couldn't see anything anymore. So in this particular example, the original diagram has 26 Seifert circles. And the thing I have shown there is a reduction of these 26 to 20. And then there are 8 arcs, which are sort of bold, and that gives you 8 additional moves, and that gives you 12 Seifert circles. And that is a diagram which has a minimal number of Seifert circles. And so the formula we have is essentially you get 1 plus the summation of these alpha i's, which is 3, 4, and 4, which is 11, and then plus 3 for beta, and then minus the minimum of these alpha j's, which is another 3, and so you get 12, and that matches. Why does this happen? So remember, I told you that we're sort of doing induction. And so assume that you have 2 positive columns and 1 negative column. And you start induction on alpha 2, starting with alpha 2 equals 1. And so when you smooth the crossing in alpha 2, you get a torus knot of 2 alpha 1 minus 2 alpha 2. 2 alpha 1 minus 2 beta 2. And if you change the sign of that crossing, then you get a connected sum of torus knots. If you compare that with the case below, where essentially you have 2 negative columns, then the smoothing just does away with the alpha 2 column, but you remain in the class of pretzel lengths. And so the additional cancellations you get in this case when you have only 1 negative column, which results from the fact that the thing collapses to a single torus knots, that's the root cause why you get additional reductions in the case when you have a single negative column. And these things propagate essentially through this induction. Okay. I'm almost, I have just 10 minutes left. So I want to briefly talk about the last case. The last case is the most complicated by a long shot. Okay. And you see there's a formula which, again, it would take some studying of what this formula actually says. And so I want you to look at just closely at the bottom two lines in this slide. So if the diagram is alpha alternating, and so there are no negative parallel crossings, and there are no positive anti-parallel crossings, then this is an alternating diagram. And there still might be some reduction moves possible, and that comes from the fact that we allow these mu i's to be 1. And so delta plus is the number of mu i's which are just +1. And they will result in some additional reduction moves. If there are no such ones, so if all the parallel columns have at least 2 crossings, then this delta plus is 0, and you get a relative simple formula. Now, notice that in this theorem, I have that that the parallel columns, that the number of parallel columns is at least 4. Remember, the number of parallel columns has to be even. So the difficult case, if there is only 2 parallel columns. And out of those cases, when there are only 2 parallel columns, I will show you only a single one, and that's the most interesting. So here it is. And I only want you to concentrate in that formula 5 on the top 2 lines. So the first thing here is that we no longer have the braid index is equal to something, but the braid index is an element of a set. And so what you see here is that the difference between the 2 numbers in the set is 1. So the method fails. The diagram we can draw and the bound we get from the Homefly polynomial sort of differ by 1. So the method fails. Now, if you look at the very top line of 5, so I'm only going to now talk about the top line of 5. So you have 1 negative column, and no, sorry, you have two parallel columns, and the key is that the number of crossings in these parallel columns differs by exactly 1. So this is mu1. No, v1 equals mu1 plus 1. So the difference is exactly 1. And then we have a restriction on these alphas also. Then this happens. So just about the smallest example of such a thing is the link L9 n non-alternating 15 1. And in our notation, is a parallel column of 2, a parallel column of -3, and then a anti-parallel column of 4, which is positive. If for this particular link, the Homefly bound gives you 3, the diagram bound is 4. And so we could not resolve this. Now, what we did do in this particular case is we essentially computed the Homefly of the parallel double. So if the braid index is 3, then the Homefly of the parallel double will have a braid index of 6. But the Homefly computation yielded 7. So we know the braid index could not have been 3. Here's a bunch of other examples where we did the same calculation. And so look at the last one, 4, -5, those are the parallel columns, 4, 4, 0. And so the double had a braid index of 11. And so basically, if you look at from the antiparallel columns, you get 2 plus 2, which is 4, plus 2 is 6. And essentially, since the double had a braid index of at least 11, it could not have been 5. And so you give 2 plus the summation of these alpha j's. For all examples where we have tried where the minimum alpha j is greater or equal to 3, this calculation failed. So what did we do in these cases? Well, if the minimum of these alpha j's is 6, we looked at the parallel triple. And so if I walk you through the last example, there was triple I. So the formula from the 6 and 6, you get 3, 3, which is 6, and then plus 2 is 8. If it would have been 7, then basically the B naught would have been 21. But by 22, it tells you it can't be 7. And so these examples failed. They were inconclusive whenever this alpha j was greater or equal to 4, the minimum. Just to look at this last examples, the triple in this case has 171 crossings. And so that's sort of getting to the bound of what is computational on a laptop possible in terms of computing the home flight polynomial. And so we conjecture that in this particular case, actually 2 plus the summation of the alpha j is actually correct. But we have no evidence for this besides these computations I've shown you. And the last thing I want to show you is our methods in terms of doing any kind of induction on the diagram of this double, they fail. Why do they fail? Well, each crossing now has become 4 crossings. And if you just think about taking one of such a quadruple of crossings and you want to change its sign or smooth it, then you essentially obtain a link where you have no idea what kind of class this link belongs to. Okay, and we don't know what actually a minimal diagram of such a thing would be in the first place. And so we have no handle on getting actually bounds on the upper and lower bound of the home flight polynomial for such a link family. So the method we have used basically breaks down completely. And we have similar conjectures for the other cases. The last thing I want to point out is this was sort of sub-case 5. And so basically that sort of tells you that in the case when the number of parallel columns is 2, the formulas we obtain are very, very complicated. And but we resolved it in all cases with the exception of this case 5. And so Jason's question was very right on. We were barely able to do this for non-alternating pretzel links. Non-alternating Montesinos lengths will be much, much more difficult. So, thank you.
Well, Klaus, thanks for a great talk. And now the floor is open for questions.
Klaus, I have a rather naive question for you. I don't remember now the knot. I mean the first part and sets of the knot table so well. Do you have 2 alternating knots and a different crossing number that are just below and above a non-alternating knot in terms of crossing number?
Okay, so the examples I had there, you mean these type of examples?
For example, yes.
So remember, the reduction moves which are possible in the non-alternating case, there are at least, they're either the reduction moves you had before or more. So basically, the braid index can be at most equal to the braid index of the alternating case. Okay, and we find many instances where the braid index is strictly less. And looking at these small examples in not info, led us naively to think that the difference would be at most 1. But as I pointed out, that even for the class of pretzel links, the difference between the alternating and non-alternating case can be arbitrarily large. Okay, and the reason we didn't find that in the table is that up to 12 crossings, that's just too simplistic. Okay, it doesn't happen for these small crossing numbers. You need to have larger crossing numbers for that difference to be more than 1.
Right. Okay. Thank you.
Yep.
Hi, Klaus. Excellent talk. Thank you very much. I really enjoy it. Well, my question is, let me see if I can put it in the right words. So you have been saying that there are some reduction moves that you apply to the knots, so you can reduce the number of cipher cycles, right?
Yep, cipher circles.
Cipher
Yep.
circles. And you use those moves to reduce alternating knots, alternating Montesinos knots. But when you try to apply those moves to these pretzels, there are a new set of moves that you need to apply in order to reduce the number of alternating, the number of cycles. Yeah. So will you, I don't know, do you think this is possible that this only set of moves are enough to reduce Montesinos knots to the minimum number of cipher cycles?
So let me put it this way. These moves are actually very, very complicated.
Oh.
I have only shown you this one example where I believe that you can, by just looking at it, sort of believe that's possible. Okay. In other examples, these moves are even more convoluted.
Oh,
okay.
yeah.
So this was extremely difficult for us to find these moves and actually sort of argue that these moves can always be done. The details are very, very tedious. So, for example, what I sort of didn't say, well, I said it briefly. The columns in this picture, they can be permuted. It has no influence on the home flight polynomial, right?
Yeah, right.
You need to argue that they can also be permuted and you can still carry out these reduction moves.
Yeah.
Okay. And so this is extremely complicated.
I see.
And so what I know is the following, that if you think of the general Montesinos case, okay, and you think of the case where you have one positive tangle and one negative tangle, and then you want to insert a third tangle, and that tangle is you start off with this tangle, let's say, having two crossings or something like that. Then if you sort of smooth this away, these two tangles could cancel each other completely. And so I think the number of reductions will be much more complicated than what happens for pretzel knots. And I wouldn't want to venture a guess of what happens. Okay, my expectation would be, since for one particular class of pretzel knots, this strategy already fails. There's certainly going to be Montesinos knot types where the strategy also fails. And at this point, we have given up on this for the time being.
Okay.
So you can find two papers about these pretzel links on the archives, and you will see they're quite long. So they're each about 30 pages, and it's quite complicated. So maybe we come back to it at some future time, but it's formidable.
Okay.
So that's a long-winded answer to your question. But no, there will be no easy classification of such moves and say those moves are enough.
Okay, thank you very much. Thanks for your answer. Yeah, it clarifies a lot. I think there is a question from Ban Pham.
Hi, Klaus.
Hi, man.
Sorry, my naive question. So the strategy that you use at the end with the non-alternating links was to double it, and apparently that failed in the proof because you couldn't classify the kind of links when you smooth the crossings. Then what worked so that you would triple it? Why the double didn't work? Why would you triple?
Let's say, why would I triple? Desperation. if we were going to conjecture, okay, if the smallest number you have, the smallest number for these alphas you have would be 8, then my conjecture would be that the quadruple would resolve that. However, you know, quadrupling things means one crossing becomes 16. And that's just simply in terms of computation I can do on a laptop in terms of the home flight polynomial completely out of reach. And so basically, we checked this out up to the range of what our computational abilities are, right? I mean, we all know that the home flight polynomial, that there is no polynomial algorithm. So even if you would go to a much faster computer, you know, maybe you could do some quadruples, but you couldn't do more than that. So we are basically, computation will not solve this problem. And our method basically doesn't apply to these doubles or triples. And I have no answer for you what you could do instead. Okay. So we stumbled upon this. This works with a double out of desperation. We wanted to see, could we decide any such case at all? Okay. And I think there are other examples where other people may have used similar methods. And so that led us to why not we give it a shot.
Thank you.
We're sitting on this case for quite a while because we thought for a while it would be so nice if we could say we completely determine the braid index of all pretzel knots. But eventually we had to say, well, this particular case, we give up, we cannot.
Well, not with this method.
Not with that method, yeah.
Thank you.
Okay, are there any other questions?
Hey, Klaus.
Hey, Björn.
Hey, good talk. So, can you elaborate a little bit more by looking at this last example here you have on the picture? So right now you have 2, -3, and 4. That's an exceptional case, right?
Right.
But maybe you also want to tell people what happens when we increase that 4 to like 6 to 8, you know, then what happens? Because I think that's also interesting.
I don't have a slide for that, so I cannot. And on top of my head, I don't remember. What I can say is when you look at this formula 5, right, you see that there is a restriction of 1 less than alpha k plus less or equal to mu1, right? And so all I can say on the top of my head is if that restriction is not valid, so if the alpha k is larger than that, then we could determine the braid index of this particular class of pretzel knots. Yunan, do you remember what happens?
Yeah, it is the smaller one.
It is the smaller one.
Yeah,
okay,
we do have that move. So the diagrammatic move, we do have an extra move to reduce that from the diagram. We actually achieve that.
Okay.
Yeah, so once that restriction is removed, then this bound is actually the 1 plus sigma alpha j.
Yeah, again, all other cases besides those in 5, we could decide. We did have reduction moves. But,
yeah, so that's what it makes
and
this so.
I didn't want to include pictures of these cases because I thought it would be too complicated.
As is, you know, hey, it doesn't hurt. It's already so complicated. But this is what makes it interesting, I think, you know, because you start with a 4, you know, there's something you can't quite decide, but then you move up, hey, suddenly no problem, you know, anymore. Then you can do it. And with all the other cases that are like that. So as you increase this number, the last number, you're okay. But then it's always within this limitation we are having difficulties. And our conjecture is that we, under this constraint, the braid index is always the larger one, not the smaller one. And the examples we use, the doubles and triples, they kind of confirm that. We just couldn't do it in general.
Yeah, that's the conjecture. It's always the larger one. But you should keep in mind that the number of this particular type of pretzel lengths of this third type is a very, very particular one, right? You have only 2 parallel columns, and the number of crossings there differs by exactly 1. So it's a very particular type.
Okay, if there are no other questions, we'd like to thank the speaker for a terrific talk.
Thank you for allowing me to talk.